start. So, Anshuman Ramalingam, please, turn is yours. Go ahead and tell us about the introduction to nuclear power reactors and their generations.
Good evening, everyone. Welcome to today's webinar. Today, I'm going to speak a few words about the nuclear power reactors and their generations. Next slide, please. First of all, let's start with what is a nuclear power reactor. The nuclear power reactor is the device which converts the nuclear energy into thermal and then to electrical energy, so it can be used by us. Usually, it's done by splitting of the nuclei, which is known as the fission. Also, there are fusion reactors, but it's still in the research process. So the thermal energy is then used by the turbines, and it's converted into the electrical energy. The reactors itself have their own advancement over the years, and that is what we are going to learn today. Next slide. So the energy production, as I said, it is done using the fission reactions, but the reaction should be controlled in order to ensure the safe and efficient operation to prevent accidents. And in this image, you can see a typical schematic of a PWR reactor. Next slide. So here, let's see how the fission reaction is done. First, a neutron bombards onto a nucleus, and that nucleus splits. During the split, it releases energy and as well as more neutrons. These newly born neutrons continue the reaction to self-propagate. So it is known as the fission chain reaction. So in this animation, you can see the reaction propagating by itself. And usually these nuclei are either uranium-235 or plutonium-239. Next slide, please. So let's move on to the generations of the reactor. Overall, the reactors can be categorized into 4 generations, starting from generation 1 up to generation 4. But right now, the commercially operating generation is generation 3 plus. And about each generation, we will look in further in the upcoming slides. So next slide, please. In this slide, you can see the timeline and some of the examples of reactors for each generation. For example, the generation 1, which are the early prototypes, the example of them are shipping port and Magnox reactors. Then the generation 2, generation 3, the 3 plus, and the nowadays under research generation 4 reactors. Next slide. Generation 1 reactors, the early prototypes. So these are the generators which were designed in 1950s and 60s. These were the foundation of the commercial nuclear power, and they were less efficient and it's non-sustainable reactors. These were the test beds which is used to build the more commercial reactors in the future. And in this example, you can see a Magnox reactor, which is built in the UK, and APS-1, the first commercially built reactor to connected into the grid in Obninsk, Russia. Next slide, please. So let's go to the second generation. This generation is the base of the reactors which are operated now. Some of them are advanced gas-cooled reactors, boiling water reactor, pressurized water reactor, and another type which is known as RBMK, the Russian BWR, and CANDU, which is built in Canada. So these were the basic reactors for the ones which are operated right now. Next slide, please. So the generation 3 reactors, as I said, these reactors were based on the second generation, but their safety, efficiency were increased, and the design were more simplified to have the sustainable and more safe operation. And due to the high efficiency, these reactors were built around the world than the generation 2 reactors. Next slide. Generation 3 plus. So now, even to increase their operational safety more, the passive systems were introduced, and the more meltdown prevention methods, the improved containments were added into these kind of reactors. Next slide, please. In this slide, you can see some safety systems in a generation 3 plus reactor, which is VVR 1200. So first of all, let's start with the barriers which were built into the system. The first barrier is the fuel pellet. The fuel pellet is the place where the fuel is stored. Then the fuel pellets are put into the cladding to form the fuel rod. The fuel rod is made into a fuel assembly and it's put into the reactor core vessel. The reactor core vessel and the water around the reactor core is known as the primary circuit. So the radioactive water is contained within the primary circuit. It doesn't go to the turbine or somewhere else. So all the radioactivity is contained within the primary circuit. Then the fourth one is the containment building. If there in case of an accident, the containment building will protect the people and the environment from the radiation with the containment building. Also, in this picture, you can see some of the safety systems which are used in the reactor. First of all, the spray system, then passive heat removal system, hydrogen evacuation system, the emergency core cooling systems, and the core melt trap. These are the advanced safety measures which are used in nowadays inside the reactors. Next slide, please. So let's go to the final generation of the reactors, the generation 4. These are in the research phase right now. These are used to increase the efficiency, the safety, and to reduce the overall waste and the sustainability of the reactors. So how to increase the efficiency? The most way to increase the efficiency is by increasing the coolant temperature, and more safety measures which are passive are introduced, and using some reactor waste, the reduced waste can be obtained. And here we consider 6 types of reactors: gas-cooled fast neutron reactor, lead-cooled fast reactor, molten salt reactor, sodium-cooled fast neutron reactor, supercritical water-cooled reactor, and very high temperature reactors. Next slide, please. Here you can see some of the 4th generation reactors, and the first one, which is built in China and under operation right now. That's the one and only reactor which is working at the moment. The rest of them are a design model or either under construction in the way. The Brest 300 is the lead-cooled reactor which is being built in Russia, and Toshiba 4S is a reactor which is being proposed prototype in Japan. Next slide. Okay, so that's all for my presentation. If you have any questions, you are welcome to ask. Okay, I think we have a question. So the difference between PWR and BVR. Basically saying BVR is a type of PWR. PWR is a variety of reactors, and BVR is one of the reactor which is built in Russia. On the other hand, there is some other reactors, PWRs, built in America, which are known as AP. AP series is built in America, and VVR is built in Russia. There are some differences. For example, the AP reactors have a vertical steam generator and VVR has a horizontal steam generator. Any more questions?
Guys, please, if you have questions, you may warmly ask. Our speaker is ready to ask your questions. Even you can write your questions in our chat. Well, we'll have next question.
So, what do you mean by the building? The containment?
I think so. No. How
The
does the building protected? Maybe, yes, the
Okay,
big one. Yeah,
can you go
containment.
to the previous slides where the containment is about the VVR? Okay, stop. So here, the containment is a strong structure. It's you can see the strength of this structure in the slide itself. So it's built to withstand strong earthquakes, tornadoes, flood, aircraft crash, and even a shock wave of a pressure of 30 kilopascals. It's a concrete structure. Concrete structure reinforced with steel. Does this answer your question? I hope so.
We have next question. What
that?
is the advantages generation for reactor? Why are there still many countries building PVR and VVR reactor?
Okay, generation 4 reactors are still under research. Most of the generation 4 reactors. Only China has built the operational one right now up to date. The other ones are still either being under research or under construction. For example, the one in Russia, Brest 300, it's under construction. The other ones are under research. And the reason for PWR or VVR, it's the most, for the commercial ones right now, that's the most advanced and safest reactors available. And the generation 4 reactors are high costly, and it needs more high temperature gas reactor. Yes, it's also a generation 4 reactor, which is under research. I mentioned it in the slides. There's no high temperature reactors except the one in China. Any other questions?
I think
I think that's
questions are all yes. If you have any questions to our this speaker, you can write your questions to our social media. We have Instagram, Telegram, VK, Facebook. We are in all social media. You can kindly write your questions to our media. And now I want to give you turn to our next speaker. Please, Lennox, turn is yours. Lennox are going to tell you about nuclear energy and climate change. Please, Lennox, go ahead.
Okay, thank you. Good day, everyone. So, thank you for joining us to today's webinar. I'm going to take you through nuclear energy and climate change. And my name is Lennox, and I'm delighted to be a presenter today for this session. So, let's begin by acknowledging the critical connection between energy production and climate change. So, I will take you through the outline of our session. So, we will start by having the talks between nuclear energy and climate change. Then we go on to the need for low carbon energy, which is our important part of the session. Then we'll then talk about nuclear energy. Please, can you go to the next slide? Okay, so that's our outline. Next slide, please. Okay, so as you can look at this image, the left side shows the effect of climate change, and the right side shows the potential of nuclear energy in correcting the effect of climate change. So, in this uh, current century that we are, at the beginning of the century, climate change was just a topic of discussion, like in existence. But and natural and disasters of climate change back then were just regarded as natural disasters. But as we move into the century, the world has embraced that they have a problem of climate change, and now climate change disasters are now called climate change effects. And from now on, many organizations such as Hope Commit have started to make strides in correcting this climate change, and we have also experienced the effects of climate change across the globe, from the southern Africa, whereby we have countries like South Africa, Zimbabwe, and Zambia having droughts, and we also have natural disasters due to climate change in parts of Asia, such as Indonesia, whereby there are volcanic eruptions, which are believed to have a possible lead to tsunamis. And now people are evacuating. And we also had the recent floods in Dubai, which are also part of the effect of climate change. So these are indications, evidence that climate change is a disaster and it's coming for everyone. So uh, now the COP committee have analyzed this situation, and they are led to believe that only energy sector among all sectors is the highest contributor with more than 30% contribution to climate change. And now there is a need to decarbonize the energy sector so that we don't suffer this effect. So the need for low carbon energy. Why do we need low carbon energy? Next slide, please. As, okay. So next slide, please. So our world is at a pivotal moment with the need for low carbon energy sources becoming increasingly urgent. Why is that? Because now the development of smart systems which require very high energy, the development of new technologies, industrial demands require more energy. For example, hydrogen production, AI development, which is growing rapidly, and also the adoption of climate change solutions which are being provided require high energy. So going forward, it is discovered that climate change will always be linked to energy production, and energy production will be always the highest contributor to climate change. So that's where there's need to pay attention to energy sector. So according to the International Energy Agency, global energy-related carbon dioxide emissions reached a high of 33.1 gigatons in 2019. Without a significant action to reduce emissions, the Intergovernmental Panel on Climate Change warns that temperatures could rise by 1.5 degrees above pre-industrial levels as early as 2030, leading to a catastrophic consequence for our planet. So that only gives us the depth in which climate change needs to be addressed. So, and that gives us the reason and need to have low carbon solutions which are sustainable. And in comparison, the renewable energy are not as sustainable as nuclear energy. That's why nuclear energy is now the net zero solution for where we are and where we are going. So, next slide, please. Amidst these challenges, nuclear energy emerges as a promising low carbon solution. Nuclear power plants generate electricity without emitting greenhouse gases during operation, making them a vital component of the transition to a sustainable energy future. Currently, nuclear energy accounts for about 10% of global electricity generation, according to the Nuclear World Association. That is. So, the environmental benefits of nuclear energy are profound, unlike fossil fuel-based power generation. Nuclear power plants emit virtually no air pollution, helping to improve air quality and reduce health risks associated with pollution. Studies estimate that nuclear power has prevented millions of tons of carbon dioxide emissions annually, and making a significant contribution to global efforts to combat climate change. So, however, the nuclear energy industry also faces challenges. And amongst this challenge, there is high lacking in nuclear facility personnel. That includes nuclear engineers and the nuclear scientists, all personnel involved in the nuclear industry, because this technology has had misconceptions and its safety concerns. So people have been withdrawing from the nuclear industry. So now that it is the solution, there is a challenge in nuclear personnel. Yet, amidst these challenges, lie opportunities for innovation and advancement. Advances in nuclear energy, which has been discussed by the previous speakers, such as small modular reactors, generation control designs, offer promising solutions to improve safety and reduce costs and enhance sustainability. So, the role of nuclear energy in national climate policies cannot be understated. Several countries have included nuclear energy in their climate strategies and commitments under the Paris Agreement, recognizing its importance to reducing greenhouse gas emissions. Forecasting suggests that nuclear energy will play a significant role in global energy in the coming decades. So, in conclusion, nuclear energy holds immense potential as a low-carbon solution to address climate change by harnessing the power of nuclear technology and paving way for a sustainable future. However, achieving this vision requires collective action and support from policymakers, industry, stakeholders, and the public by engaging in nuclear-related studies and nuclear solutions. So, thank you again for your participation in today's webinar. Next slide. Would like to take your questions, and you can keep them and write them down. And at the end of this webinar, I think there'll be a session for question answering. So thank you, and keep with us. Thank you.
Well, thank you very much, Lennox, for your presentation. I think it was such informative and useful. And yes, as Lennox said, if you have any questions, if they are small, you may ask here, or you may write down in the chat of Zoom, and we will answer your questions. Please, you are welcome. Well, if you don't have any questions, or you want to ask your questions at the end of our webinar, I'm ready to give the turn to our last speaker. So Falkenberg, please. Falkenberg is a student from Bobninski Institute for Nuclear Power Engineering, and he will be tell us about the thermonuclear fission. I think it's also one of the interesting and important specter of nuclear industry. Well, Falkenberg, please, the turn is yours. Go ahead.
Thank you very much. Good evening, everyone. All right, so I'm going to talk about thermonuclear fusion, which has also been stated that is a very crucial branch in the nuclear field. As you have seen from the previous speaker, I've talked about nuclear fission mostly, the PWRs and the first reactors that you've seen. They rely on a technology that we call nuclear fission. But again, in the nuclear sector, we also have to think about the future generation on matters sustainability, and of course, we have to ensure that the resources that are available are used in a manner that would not really interfere with the status of future generation. And so one way of ensuring that there is a case is, of course, by exploring an alternative way of harnessing this nuclear power, but by relying on resources that you would consider unlimited. Because as you have seen, the fusion technology, the fuel materials that we are using, most of them, they are limited in nature. We call them the fissile materials and, of course, the fertile materials. They are limited in supply. But when it comes to the fusion or thermonuclear fusion, we tend to explore alternatives or alternative fuels that would ensure that we have unlimited supply of electricity. So let's move on to the next slide, please. All right, so before we really get into the fusion aspect, I'd like us to understand the clear distinction between fusion and fusion. So the graph that you are seeing on the screen can be divided into three sections. There are sections of this graph constituting what you call light nuclides, and then there are heavy nuclides, and then what we have the group, what's called the ion group, constituting a tightly bound nuclides. So, sorry, is someone talking? Okay, let's proceed. So in thermonuclear fusion, we are mainly concerned with the left section of the curve constituting light nuclides, one of them being, of course, helium, or what call the tritium, deuterium, and those are isotopes of hydrogen. So in the fusion process, you can see the fusion process would give us a nuclear fusion yield that is quite huge, as also demonstrated in the graph, all the way from 2 to about 7 mega electron volts in this case. So by harnessing nuclear energy, we are simply relying on what's called the binding energy of a nuclide, which is simply the minimum energy that would require to disassemble the constituent parts of the nucleus, what's called the nucleons. So in this case, it's done by fusion, because not really by fission. The fusion aspect, we have to subject the heavy nuclides into splitting by supplying a neutron bullet, and then it splits into constituent or subsequent nuclides, also giving us neutrons, and then we end up with a chain reaction. But we can also control that in the nuclear field. But in the case of fusion, of course, we are fusing these light nuclides, and then we get the energy from them. So on a light note, that is basically what the difference between nuclear fusion and nuclear fission is. We don't really want to go into the technical details so far. All right, next slide, please. Okay, so how do we do the tapping now? Now that we know that there is a potential way of generating nuclear energy also by fusing nuclides, but how do we do it? Of course, for us to fuse this nuclides, the very first thing that has to happen is that we must have the fuel at our disposal. So the fuel that you would need is in a fusion reaction, it can begin right from the bottleneck, like what we observe in the sun. The sun is a star, and the mechanism by which it gets its energy, which is of course huge in magnitude, is by fusing hydrogen nuclides. So the sun fuses about 500 million tons of hydrogen per second. But then the challenging aspect of this is that there is enough energy for that to happen. So there's a bottleneck reaction which involves fusing hydrogen atoms, and then we end up with massive energy, which happens right in the sun. But when it comes to what you can do on the planet, is of course we don't really have that amount of energy, because you can see that hydrogen, when you're fusing hydrogen nuclei, it's like we're trying to force the nucleus to come together. But what happens in the sun is that there is enough energy, there is enough gravitational pull to ensure that that is possible. But on the planet, of course, as you know, on the planet Earth, the gravitational pull is also not that much huge in comparison to what we're experiencing in the case of the sun. So we have to, in that case, we have to rely on a device that facilitate that fusion process, what we call a tokamak, or a Russian acronym for a toroidal chamber with magnetic fields. So there is it. We need a fuel, which in this case can start from the nuclide hydrogen, or we start from what we call tritium and deuterium. But because we know that if we start from a bottleneck reaction, you need massive energy like what you have in the sun. So we have to ignore that stage on the planet and then start the reaction from what we call a tritium-deuterium reaction. So how do we get tritium and deuterium? These are materials that are not readily available. Yes, so we have to consider techniques of generating them. For instance, deuterium, we can get deuterium from seawater. In every about 6,700, approximately 6,700 molecules of hydrogen in the seawater. In that amount, one is deuterium. And so there is a unlimited supply of deuterium. In that case, we can harness it from the sea. And the case of tritium, of course, tritium is also not readily available on the surface. So we have to subject what we call lithium to high intensity flux of neutrons. So when you subject lithium to an intensity flux of neutrons, we get the tritium that we need. But the tritium, of course, is radioactive. Yes, it's radioactive, but it's not really, if you try to compare it to what we have in the fusion process, is that it's a short-lived radioisotope, about with a half-life of about 12.5 years. So that would really be a significant improvement also on the basis of the radioactive nature of used nuclear material that we have for the case of fusion reactions, or the fusion technology that we deploy. All right, so let's move on to the next slide, please. Okay, so there are three main techniques. Actually, there are two main techniques that we have or that we use in the fusion technology in order to harness this energy. There is what we call the magnetic confinement fusion. We also have what we call inertial confinement fusion. And of course, it's really I would consider it a technique in this case, but it's an area that is being explored in the fusion technology right now, what we call the muon catalyzed fusion. So the magnetic confinement fusion, this is just a way of using magnets, so very powerful magnets to confine the plasma that we are using, because the plasma itself has very high temperatures. You can imagine what is happening on the surface of the sun. The surface of the sun is approximately 5,700 degrees Kelvin. But then on the surface of the Earth, we haven't really gotten to that point in the nuclear industry where we have materials that can withstand these extreme conditions associated with plasma. And so we have to organize our device in a way that we can control the geometry of the fuel. And one way of doing that is using magnets. Of course, plasma is ionized gas. So we can control it with magnets, very powerful magnets. And that is basically what a magnetic confinement fusion is all about, or what we call the tokamak in Russia. Okay, let's move on to the next slide, please. Yes, the second technique for harnessing fusion is what we call inertial confinement fusion. In inertial confinement fusion, we're just using, instead of using magnets, now we are using lasers. But then the lasers, about 200 sources of lasers with very high energy lasers focused to a very, very tiny point where the fuel is. So the fuel is organized into pellets, very small ones, deuterium tritium, call them deuterium tritium pellets. So the fuel is very tiny. I think it's about the size, the thickness of your air. So imagine substituting that in a point source, substituting pellets that are about the size of your hair in a point source. It becomes very challenging. So that is a challenge again right now in inertial confinement fusion. But of course, this is a technique that deploys lasers to facilitate the confinement of fusion. And this is a technique that is deployed in, for instance, this facility in the US, we call it the National Ignition Facility. And there's one, of course, I think that is the facility that so far has given us some significant results as far as inertial confinement fusion is concerned. And of course, for magnetic confinement fusion, we have the JET laboratory, or the Joint the torus, and of course we also have the ITER, or International Thermonuclear Experimental Reactor, which we'll talk about briefly. Sorry
Yes, all right.
about that. I had a technical hitch. Let's proceed further. So I was talking about what was it? Was it non-catalyzed fusion? I was talking about, yeah, the significant improvements. Go back to the previous slide, please. I'm really sorry for the technical hitch. All right, so in inertial confinement fusion, so far, the significant contribution that you've had from this, the significant results that you've had from this is about 59 megajoules output out of 11 megajoules heat from the lasers. So if you try to do that into the Q value, if you try to compute the Q value for that, it's approximately 5, I think. No, actually, no. Yeah. So Q value is approximately 5 in that case. A Q value for 5 has been achieved by both, even in the case of magnetic confinement fusion. And so this is really promising, because for the magnetic confinement fusion, the target is about 50. We need to supply about 50 megawatts of power in order to get about approximately 500 megawatts. So the target is a Q value of 10. So there are significant improvements in both cases. The JET laboratory has recorded a Q value of about 5.3. So yes, we are headed to that direction. So let's move on to the next slide, please, in the case of non-catalyzed fusion. So in non-catalyzed fusion, this is, it's really not, there are no practical aspects of this that have really been deployed so far, but it's a promising area, and it's also an area that's worth exploring, especially if you are an individual who's interested in maybe pursuing research in the fusion area. In the moon catalyzed fusion, what we're basically doing is we are substituting the electron with a muonic substance. So the muon is it's also a subatomic particle, just like an electron, but the main difference is that it's about 200 times heavier than the electron, and the half-life is about 2.2, I think, by 10 to the -6 seconds. So, and it's negatively charged just like the electron. So the significance of using a muon instead of an electron in these reactions is that if we do the substitution, we end up with either forming a muonic molecule, which constitutes the muon and the deuterium, or the muon and the tritium. And the significance of doing this is that you'll end up with the fusion reaction happening almost instantly. And it's something that can happen at very low temperatures, even temperatures that are lower than room temperatures. So it's one area that would really be crucial, due to the fact that we get the fusion reaction happening instantly and also at low temperature. So we don't really have to worry about that much about the material, the structural aspects of the device, the extreme conditions associated with these materials. With the reactions that come forth. Let's move on to the next slide, please. All right, so far, the one practical device that we have, other than also what you have in the National Ignition Facility for the use of lasers in confining plasma, is the ITER. The ITER is an international project, what's called the International Thermonuclear Experimental Reactor. And this is one project that we'll try in due time, we'll try to prove the feasibility of using fusion for commercial purposes, using fusion to supply and to give us unlimited supply of energy. So in ITER, the technique that they deploy is the magnetic confinement fusion. Like you said, in magnetic confinement fusion, you're basically using very powerful magnet to confine the plasma. But of course, the challenging aspect of this is still is a material, and at the same time also getting a sustained fusion reaction, because I think the JET laboratory has given us, also been able to give us about 59 megajoules of power from, no, not megajoules, sorry, 59 megawatts of power from 11 megawatts of power. So, but then the reaction took a very few seconds. I think it was about 5 seconds. So we need a sustained fusion reaction. And so we have to rethink several things. We have to rethink the fuel, we have to rethink materials, especially the materials that we are using because of the extreme conditions associated with the plasma or the resulting nature of the environment in this case. So that is what the ITER device is really about. We are trying to solve these issues, the material issues, the fuel issues. And of course, like we had said, even for the case of the fuel, we need to rely on other materials like lithium. So for instance, we have to, in the tokamak, we have to create a lithium blanket, but then we can make this reaction also sustainable by relying on the neutron that you get from the reaction itself, rather than relying on neutrons from an external source in order to facilitate the fusion reaction, because you would need the neutron to do that, or a neutron to be absorbed by the lithium in order to get tritium out of that. So that is what we call fusion breeding. So fusion breeding can be facilitated internally within the device itself without relying on an external source of neutrons for the fuel. So that is what ITER is all about. So again, the targets of ITER, of course, as you can see, is that we are targeting about 500 megawatts from 50 megawatt input, and also trying to demonstrate how feasible the tritium production within the vacuum vessel would be. And this is really a collaboration between 35 entities and about 7 member states. Let's move on to the next slide, please. So these are the member states that you have and the tasks that have been assigned to them. I saw it really crucial to show you this slide just to indicate the collaboration that is going on in the nuclear field right now. As you can see, these are 7 countries: Russia, China, India, United States, Japan, Korea, and the European Union. They all have components assigned to them, the components of the tokamak assigned to them, and they're working on this in collaboration in order to ensure that we have a fusion device that can give us unlimited supply of electricity that we need. Let's move on to the next slide, please. All right, so these are the future benefits. Here are some of the benefits of ITER that we intend to get from this. So there's the very first one that I really like to talk about is unlimited supply of energy, which would involve, of course, we have seen that the materials that we are relying on in this case, there is abundant supply of these materials. There is abundant supply of lithium on the crust. There's abundant supply of deuterium from the sea. And so this ideally can give us unlimited supply of electricity. So that goes to SDG number 7, affordable and clean energy. Then we also have, of course, radioactive waste eradication. As you have seen in the fuel cycle involved in this case, the only radioactive material that we're dealing with, of course, one is tritium. But as you have seen, tritium is not a long-lived radioisotope. It's short-lived. It's about the half-life of tritium is about 12.5 years. So we can really consider this eradication of long-lived radioactive waste if we try to do the comparison with what you have in the nuclear fuel cycle in the case of fission technology. All right, then sustainability. This is, of course, there is unlimited supply of electricity from the fusion, and so we would expect improvement in the infrastructure that we have in our cities. If your country is planning to construct maybe a smart city, then in the future, we would have unlimited supply from the fusion technology, which is also the core elements of a smart city. Then there's also combating climate change. Of course, thermonuclear fusion is a potential strategy for that, low carbon emissions and so forth. And also, in addition to that, in sustainability, we've also talked about breeding. We call fusion breeding. So in fusion breeding, rather than relying on external sources of neutrons, we do the breeding within the device itself. So we rely on the stray neutrons that come from the deuterium-tritium reaction again to be absorbed by the lithium blanket, and then we end up with the tritium. So it's really something that happens within the device itself. And of course, from the economic perspective, yes, we'd also consider that economical. And so these are some of the future benefits that you would expect from ITER and in entirety for the fusion or the thermonuclear fusion aspect. Otherwise, that is all I had for you today. Unless there's a question from the audience, I'll be willing to take a few questions. Or if you, let's move on to the next slide, please. I think in the next slide, there is an email. Yes. So if you have questions, you can also forward them to my email address as provided in the slide. Thank you very much for your attention.
Well, great job, Falkenberg. Thank you for your such an informative presentation. As for me, it was really, really useful. I know about a lot of useful things, information about the ITER project, and I hope for other participants so. Well, guys, if you have any questions, please, you are welcome. You may ask. Our speaker is ready to answer your questions. And also, you may write your questions to our chat, or as Falkenberg said, you may write your questions to his mail or in our social media. Well,
all right. Not really. So far, there are no fusion reactors, of course, that are generating electricity on a commercial basis. No, they're really experimental. Even the fusion devices that you have, the fusion device that you have in China, still experimental. ITER, experimental. The National Ignition Facility, experimental. They're still trying to demonstrate the feasibility of this technology being useful in power supply. And so up to this point in time, not really. But the significant, like I said, the significant results that we have so far have given us about Q values of up to 5, which is very promising. And like you say, the target, like the JET facility, as you remember, gave us about 59 megawatts. That was in way back in 2022. We had 59 megawatts of electricity out of 11 input, 11 megawatts of electricity. So that is promising from the JET facility. And of course, I'm very sure that in what we'll have when ITER goes on, when it's fired on next time, I think we'll really have significant results from them, because we also learn from these results. We learn from what was wrong, or really the improvements that we can do so far. So up to this point in time, yes, there are no fusion devices that are generating electricity for commercial purposes. None. They're experimental, and they're only being used to demonstrate the fusion aspect. And of course, the very last concept that I gave, the deuterium, the muonic catalyzed fusion, that is entirely theoretical. It's something that would be useful in the future too. I don't know if that really answered your question. Hello?
I think, yeah, we can hear you.
Okay.
I think you answered the question. Here, I want to mention the word, one of my friend's word. He said that if you think that you didn't achieve anything in this life, please look at the ITER project. They are still trying and trying. There is no result.
Yeah, I think, but I'm positive there'll be really good results in the future. We have to think ahead, because the main issue that we are really dealing with at this point in time, of course, is the material aspect. We really have to rethink our materials, because up to this point in time, we don't really have a material that can withstand a very direct manifestations like what you have in the sun. Yeah, so yeah, it's if we solve the material aspect, I'm convinced that we'll solve the fusion problem.
Well, I hope so. So guys, please ask your questions. You're welcome. As you see, our speaker is really ready to ask your questions. Well, if you don't have any questions, or you will have questions later, yes, maybe. As I said, you may write your questions to our social media. Please follow us. We are in every social media, as you see in the QR codes, on Facebook, on Instagram, on VK, on YouTube. Please follow us. We will share you. We will tell you about the nuclear industry, about the nuclear education, and I think you can find useful things, and you may increase your knowledges in nuclear industry with us. So thank you guys. Thank you for participating in our webinar, and we will wait you in our next webinars. Thank you for your attention.